There is an object right now, at this very moment, moving through the darkness between the stars. It is not a comet. It is not a natural body born from the churning violence of a young solar system. It is a machine built by human hands, weighing less than a small car, powered by the slow radioactive decay of plutonium. And it has been traveling away from Earth for over 4 decades without stopping, without slowing, carrying with it a golden record encoded with the sounds and images of a civilization that sent it out and then watched it disappear. Voyager 1 is the most distant human-made object in the history of our species. And the truth about what that actually means, the physics of where it is, how long it took to get there, and what it would take to ever reach anything beyond our solar system is far more humbling and far more unsettling than most people have ever been told. Let us start with a number. Voyager 1 is currently more than 23 billion kilometers from the Sun. That sounds enormous. And by the standards of everyday human experience, it is completely incomprehensible. But here's the thing about distance in the cosmos. The moment you step outside our solar system and look toward the nearest star, that number, 23 billion kilometers, becomes almost embarrassingly small. The nearest star to our Sun is Proxima Centauri, sitting at a distance of roughly 40 trillion kilometers. Voyager, traveling at about 17 kilometers per second, the fastest speed any human-made craft has ever sustained, would need approximately 73,000 years to cover that distance. 73,000 years. Modern human civilization, everything from the first cave paintings to the construction of every city on Earth to every war ever fought and every symphony ever composed, fits inside a time frame of roughly 10,000 years. We are talking about a journey 7 times longer than the entire sweep of recorded human history, and we have not even left our own cosmic neighborhood. This is not a failure of engineering. This is not a problem we can solve by building a faster rocket or finding a more efficient fuel. This is the geometry of the universe itself speaking to us, telling us something profound about the nature of space and the position we occupy within it. Einstein understood this in a way that cuts even deeper than mere distance. Space is not a passive backdrop. It is not an empty stage on which events unfold. Space is a physical thing, a fabric that can stretch, curve, and respond to the presence of matter and energy. And the sheer scale of that fabric, even just in the region we can observe, is so vast that the question of how any civilization could ever truly traverse it runs directly into the laws of physics at their most fundamental. Think about what Voyager actually experienced during its journey. When it launched in 1977, engineers used a rare alignment of the outer planets, a configuration that only repeats every 175 years, to slingshot the spacecraft from one planetary gravity well to the next. Jupiter bent its trajectory and boosted its speed. Saturn did the same. Each gravitational encounter was a masterpiece of orbital mechanics, a precise dance between the spacecraft and worlds, thousands of times more massive than anything we have ever built. And yet, after all of that, after extracting every possible kilometer per second from the gravitational fields of our solar system's giants, Voyager is still, in cosmic terms, essentially parked in our driveway. Now consider what the fabric of the cosmos is actually made of at this scale. Voyager crossed the heliopause in 2012, the boundary where the sun's solar wind no longer pushes back the interstellar medium, and it entered what we call interstellar space. But interstellar space is not empty. It is threaded with magnetic fields, sprinkled with charged particles from ancient stellar explosions, and permeated by a faint but detectable radiation environment. The data Voyager sends back from this region, traveling at the speed of light and still taking over 22 hours to reach us, has revealed that the transition from our solar bubble into the broader galaxy is not a sharp edge, but a dynamic, turbulent boundary. The cosmos does not have clean lines. It breathes and churns at every scale. But let us return to the terrifying arithmetic, because the distance to Proxima Centauri is only the beginning of the problem. Our entire solar system sits within the Milky Way galaxy, a structure containing somewhere between 200 billion, and 400 billion stars spanning a diameter of roughly 100,000 light years. 1 light year is the distance light itself, traveling at nearly 300,000 kilometers per second, covers in an entire year. That is approximately 9.5 trillion kilometers. The Milky Way is 100,000 of those. Voyager, at its current speed, would take about 2 billion years just to travel from one side of our galaxy to the other. Our sun is about 4.5 billion years old. The entire history of Earth fits inside that travel time twice. What does this tell us? It tells us that the universe is not built on a human scale. It is not built on the scale of our ambitions or our imaginations or even our mathematics, though mathematics gets closer than anything else we have. The universe is built on a scale that makes our most extreme technological achievements look like a child taking one step in the middle of a continent and declaring the journey nearly complete. Einstein's special theory of relativity adds another layer of constraint that makes this even more sobering. Nothing with mass can reach the speed of light. As an object accelerates toward that cosmic speed limit, its effective mass increases, and the energy required to push it further grows without bound. You could pour every joule of energy our civilization produces across its entire history into a single spacecraft and not get it to light speed. The universe has written this into its most fundamental equations, not as a technological barrier, but as an absolute physical law. Now, here is where it becomes genuinely strange, because relativity also tells us that for a hypothetical traveler moving at a substantial fraction of the speed of light, time itself would pass more slowly. This is not a science fiction idea. This is a measured, confirmed consequence of how space-time geometry works. Clocks on GPS satellites have to be corrected for relativistic time dilation every single day, or the entire navigation system would drift into uselessness. So imagine for a moment a spacecraft that could travel at 90% of the speed of light, something we have no idea how to build but can analyze theoretically. At that speed, a journey to Proxima Centauri would feel to the crew like it took just over 2 years. But back on Earth, 4.5 years would have passed. Go further, to the center of the galaxy, 26,000 light years away. At 99.9% of the speed of light, the crew might experience a journey of roughly 1,000 years. But Earth and everyone on it would have aged 26,000 years. The civilization that launched the ship would be unrecognizable or extinct by the time the ship arrived anywhere worth going. This is the cosmic trap that the fabric of space-time sets for any species trying to explore it. Either you travel slowly and the distances are impossibly large, or you travel fast and time becomes your enemy in a different way. The universe seems almost deliberately constructed to keep its contents isolated from one another. And Voyager, our greatest achievement in physical exploration beyond our own world, illustrates this with a kind of brutal honesty. We managed to reach interstellar space. We managed to send a message in a bottle into the dark. But the bottle is moving at a speed that is, relative to the scale of the cosmos, essentially zero. If the Milky Way were the size of North America, Voyager would have traveled about the width of a human hair from its launch point. There is something even more disquieting to sit with here. The golden record aboard Voyager contains greetings in 55 languages, music from dozens of human cultures, the sounds of rain and surf and wind and laughter, the brain waves of a person in love, diagrams showing where our solar system sits in relation to nearby pulsars so that any civilization that finds it might know where we came from. It is a message sent with full knowledge that it will almost certainly never be found. The nearest star system it will pass, if we can call it that, is a red dwarf called Ross 248, and it will come within about 1.5 light years of it in approximately 40,000 years. Not close enough to enter its planetary system. Just a passing glimpse across an enormous gulf. The golden record is almost certainly the longest-lasting artifact our civilization will ever produce. In 5 billion years, when the sun begins to expand and the inner solar system becomes uninhabitable, Voyager will still be drifting through the galaxy, essentially intact. carrying with it evidence that something once lived and thought and loved on a small rocky planet orbiting an ordinary star. Long after every trace of us has been erased from the surface of Earth, this small machine will persist. And that brings us to what the physics of Voyager actually forces us to confront about our place in the cosmos. We are not at the center of anything. We are not in a privileged location. We are on a planet orbiting a star that sits about 2/3 of the way out from the center of an unremarkable spiral galaxy, itself one of an estimated 2 trillion galaxies in the observable universe. The observable universe meaning the part we can see, because light from it has had time to reach us in the 13.8 billion years since the Big Bang, is a sphere roughly 93 billion light years in diameter. Beyond that boundary, space continues, almost certainly, but light from those regions has not yet had time to reach us. It may never reach us, because the universe is not only vast, it is expanding, and in the regions far enough away, that expansion is carrying space away from us faster than light can cross it. Einstein's general theory of relativity describes this expansion not as galaxies flying through space, but as space itself stretching, the fabric growing larger, carrying galaxies along with it the way dots on the surface of an inflating balloon move apart even though no dot is doing the moving. The energy driving this expansion is what cosmologists call dark energy, a term that honestly functions more as a label for our ignorance than a true explanation. It fills the vacuum of space and acts as a repulsive force at cosmological scales, accelerating the expansion of the universe rather than slowing it. The consequence of this acceleration is that the observable universe is effectively shrinking over time. Galaxies that are today near the edge of what we can see will eventually recede beyond it. In the extremely far future, any civilization looking out at the sky from inside the Milky Way will see only a dark and empty cosmos, with no evidence that other galaxies ever existed, because they will all have been carried beyond the observable horizon. Voyager is traveling in the wrong direction and at the wrong speed to reach any of this. But Voyager was never really about reaching another star. It was about something more immediate and more profound. It was about learning what lies just beyond our own doorstep. And what it found there is strange enough. The heliopause, that boundary where our sun's influence ends, is not a smooth shell. It is asymmetrical, distorted by the flow of the interstellar medium, pushed in on one side and extended on the other. The magnetic field outside it is aligned differently than we expected. The density of cosmic rays changes abruptly as you cross the boundary. Our solar system is moving through the galaxy at roughly 220 kilometers per second, and that motion carves out a wake in the interstellar medium, a kind of bow shock in front of us and a long tail trailing behind us. We are not sitting still. Nothing in the cosmos sits still. Every object is in motion relative to every other object, and the geometry of that motion is governed at every scale by the same gravitational equations that Newton first wrote down and Einstein later showed to be incomplete descriptions of a deeper geometric truth. What Voyager taught us, and what it continues to teach us with every data packet it sends home before its power finally fails sometime in the mid to late 2030s, is that the transition from the known to the unknown does not happen all at once. There is no sharp line where the familiar gives way to the alien. There is a gradual, complex, richly structured transition zone full of physics we are still working to understand. And if that is true for the relatively short step from our solar system into the interstellar medium, how much more complexity must lie in the vast, largely unexplored stretches of the galaxy beyond? We have visited 8 planets in our solar system with robotic spacecraft. We have landed on 2 worlds beyond Earth. We have sent 1 probe into the space between the stars. The rest of the cosmos, the overwhelming, almost incomprehensible remainder of it, is known to us only through light, through the photons that have crossed unimaginable distances to fall into our telescopes and tell us, in the language of wavelength and frequency and intensity, something about where they came from. And light, remarkable as it is, has limits as a messenger. It tells us about surfaces and atmospheres and temperatures and chemical compositions. It does not tell us what it feels like to stand on the surface of a world orbiting another star, or whether the water in a distant ocean is cold or warm, or whether the rocks beneath it are geologically active or dead. Those things require proximity. They require presence. And presence, given the geometry of the cosmos, is very nearly impossible to achieve. Voyager understood this, in a sense. Its instruments were designed to measure, to record, to transmit. It was presence in a minimal but real form, a human artifact in a place no human eye has ever seen directly, no human hand has ever touched, no human foot has ever stood. And it will keep moving, keep drifting, long after the civilization that built it has ended or transformed into something we cannot currently imagine. The terrifying truth about Voyager is not that it failed. It is that it succeeded beyond all reasonable expectation, crossed into interstellar space, and still barely moved the needle on the cosmic scale. It is that the universe is so large and the laws of physics so constraining that the most ambitious act of exploration our species has ever managed registers as essentially zero on the map of what exists. And yet there is something in that which is not simply terrifying. There is something that is also, if you let it in, deeply clarifying. We are small. Our reach is limited. The cosmos is vast beyond any intuition we naturally possess, but we measured it, we calculated it. We built a machine that crossed the boundary of our solar system, and we sat here on this small planet and received its data and knew what it meant. That capacity, the capacity to understand a universe so much larger than ourselves, to hold in our minds the geometry of space-time and the physics of expansion and the loneliness of a probe drifting through interstellar darkness, is itself extraordinary. It does not diminish the vastness of the cosmos, but it suggests that something remarkable happened on this planet, something worth understanding more deeply, something worth continuing to explore, even knowing the full, humbling scale of what we are exploring.